Good afternoon, everyone. Myself, Manoj Kumar, Associate Professor in the Department of Mechanical Engineering, IIMT, College of Engineering, Greater Noida. Today, we will discuss the Rankine cycle. So, let us start the discussion. Topic of today's discussion is the definition of the Rankine cycle, the working principle of the cycle, the component of the Rankine cycle, the working of Rankine cycle, energy analysis of the Rankine cycle, the efficiency, the first life efficiency. Basically, we will discuss the first life efficiency of the Rankine cycle, the ideal Rankine cycle, the regenerative cycle, that is the modified version of the Rankine cycle, and the combined Rankine cycle, that is the combination of gas turbine and steam turbine, means GTST turbine. So, what is Rankine cycle? Basically, when Carnot cycle is modified for the vapor power cycle, then this cycle is called the Rankine cycle. Basically, Rankine cycle is the ideal cycle which is the used for the power plants. So, basically, Rankine cycle, what is working principle? Basically, Rankine cycle is the heat engine cycle where the working fluid is basically it changes the phase. So, component of the Rankine cycle are basically there are four components: the boiler, the steam turbine. Turbine may be impulse turbine or reaction turbine, the steam condenser, and the feed pump. So, let us discuss the processes in the cycle. So these four components, there are various processes like the process 1, 2 that is occurring in the pump, where this is the isentropic process, means the compression is reversible and adiabatic. We are compressing water, pumping water reversibly adiabatically. Then reversible and adiabatic combined. So therefore, this cycle becomes this process becomes isentropic process. Means there will not be any change in entropy. The second process that occurs in the boiler, the process 2, 3, that is shown in the TS diagram as well as the schematics. So in this process, we supply heat and the high pressure, high temperature steam is generated. This high pressure, high temperature steam which is generated in the boiler is expanded in the turbine. So this expansion in the turbine, that is the process 3, 4, is also isentropic process. Isentropic means this process is occurs reversibly and adiabatically. Adiabatic means there will not be any heat transfer from the turbine or to the turbine, and reversibly means there will not be any entropy generation. So this process is reversible adiabatic. That is why this is called isentropic process. And process 4.1 that occurs in the condenser, we can say that this is the constant pressure heat rejection process, where the heat is rejected and the steam is condensed into the saturated liquid. The steam is allowed to condense into saturated liquid water at state 1. This condensed liquid is further pumped with the help of pump to the boiler, and in this way the cycle is repeated. So there are four processes in the Rankine cycle: the two reversible adiabatic and two reversible isobaric. Means the process in the boiler and condenser are isobaric, and the processes in pump and turbine are reversible adiabatic, that is isentropic. Yes. So if we compare the Rankine cycle with the Carnot cycle, so in the Carnot cycle, heat addition and heat rejection are isothermal, whereas in the Rankine cycle, heat addition and heat rejection are isobaric. So the only difference is in the heat addition and heat rejection, while the other two processes like expansion and compression are the common. Both are in the both the cycle. In Rankine cycle, it is reversible adiabatic, and in the Carnot cycle also it is reversible adiabatic. So in the Carnot cycle there are four processes. In Rankine cycle there are four processes. In Carnot cycle, two processes are reversible adiabatic, and in Rankine cycle two processes are reversible adiabatics. So the Carnot cycle and Rankine cycle both have the two common processes, that is reversible adiabatic processes, and the difference is in Carnot cycle, heat addition and heat rejection are isothermally, whereas in the Rankine cycle, heat addition and heat rejection are isobarically. Let's move further. So the working is this: the process start with the feed pump, like here in the previous So the heat addition in the process start with the feed pump, means we will pump the saturated liquid to the boiler, and in the boiler heat is added, and the high pressure high temperature steam is uh, generated. This high pressure and high temperature steam is expanded in the turbine, and this after the some work is developed in the turbine, and the low pressure low temperature steam is supplied to the condenser, where it is condensed to saturated liquid water. This liquid is further pumped to the boiler. So in this way the cycle is repeated in the four components. So working fluid that carries heat from the boiler, and some of heat is converted into work in the turbine, and remaining heat is rejected in the condenser, where steam by rejecting heat to the surrounding atmosphere is condensed. This condensed liquid water is again pumped to the boiler. So the cycle is repeated in this way. So let's so the analysis of the cycle. So this the H1 equal to HF. What is HF? Basically, the HF is the saturated liquid. Saturated liquid means what? The in the Rankine, since Rankine cycle, in the Rankine cycle we are using vapor. So vapor sometimes uh, condenses. So there is a bell-shaped region. So on the lowermost corner, so the situation the water, the saturated water, that is they at condenser pressure. HF, how we will find HF? HF is the enthalpy of saturated liquid at condenser pressure. So HF, from there we can find from the steam table. Actually, in the gas turbine we will have PVT and relationship, and from their relationship, thermodynamic relationship to find. But for the vapor power cycle, we don't have apply these relations, because in the vapor power cycle the steam sometimes working fluid is in the form of steam, sometimes in the vapor, sometimes the mixer. So we cannot apply certain principles. So in that way, there is a table called steam table. So we find the values uh, from the steam tables, from the various steam tables. In that way, uh, you can have a purchase a steam table in SI units, and further from the problems, if suppose problem is given that the steam is expanded from 10 bar 300 degrees Celsius. So from 10 bar 300 degrees Celsius, this data, all the data, this is at 10 bar and 300 degrees Celsius, you will have enthalpy, entropy, every properties is tabulated in the table. So you can find values from the table and then calculate it. So from saturated liquid is treated as there is a table, the first property HF. So you can find from the saturated steam table, and the pump work is generally all the properties. So like the steam generated in the boiler. So steam is generally the steam generated is superheated, yeah, dry, saturated, or even the wet. So we know the condition. So that from the table you can easily calculate it. Similarly, the expansion in the turbine is isentropic. So if you equate the entropy, you will find dryness fraction, the condition at the state 2, that is after at the turbine exit. So you can also find the H2. For S3 can also be found, but H4 means the after the compression of yeah, pumping of the water. So that is in the some limited space. So for to calculate that, generally for the low pressure cycle we uh, we neglect the pump work. But if you have to calculate the pump work anyhow, so we can calculate the pressure difference, means the high pressure minus low pressure, means what, the boiler pressure and condenser pressure into the vf is what, the value of saturated liquid, volume of saturated liquid at condenser pressure vf. And since generally, in general, the pressure is given in the bar, so we have to calculate that into the pascal. So to convert this pressure, we have to multiply into the 10 to the power 5. Again, the enthalpies are tabulated in the kilojoule. So we have to convert this pump work also in the kilojoule. So to convert this pump work into kilojoule, you have to divided by 1000. So generally the pump work will comes out the VF into the pressure difference, that is the high pressure minus low pressure, or we can say the boiler pressure minus the condenser pressure into the 100. 100 why? Because 10 to the power 5 divided by 10 to the power 3, so it will comes out 10 to the power 2, that is 100. So in that way you will find the pump work. Similarly, heat addition in the boiler. Heat addition is what? So when water enters the boiler with certain enthalpy, and when we heated the water, so after heating, the saturated superheated steam is generated. So the enthalpy of steam minus enthalpy of water, this will gives you the heat addition in the boiler. So since this process is reversible isobaric, in isobaric heat addition, so isobaric heat addition is equivalent to the change in enthalpy of the fluid, that is the uh, superheated steam, enthalpy of superheated steam minus the enthalpy of the liquid which is enters the boiler. This will gives you the amount of heat added in the boiler. Similarly, heat removed in the condenser. Since in the condenser saturated liquid enters, and after the condensation, this liquid become this saturated vapor enters, and this saturated vapor inverts the saturated liquid. Since there is a condensation, so the latent heat rejected by the liquid is called the heat rejection in the condenser, that can be calculated by the change in enthalpy of the steam entering the condenser, that will comes out the heat rejected. So a turbine work output, turbine, since expansion in the turbine is reversible adiabatic, so if you apply the steady flow energy equation, this and since the fluid entering the turbine and leaving the turbine having negligible velocity and almost at the equal height, so there will not be any change in uh, potential energy as well as kinetic energy. So the only factor remains is only factor remains is the work, turbine work, enthalpy components, and heat transfer is also negligible because uh, since expansion is reversible adiabatic. So adiabatic means there will not be any heat transfer, that is isentropic. So only the work component and the enthalpy components remains. So the turbine work will comes out this the enthalpy difference, the enthalpy of steam entering and enthalpy of steam leaving the turbine, that is S3 minus S4. Okay. So in that way, so since this analysis is based on the per kg mass flow rate, so we if we know the mass flow rate of then we multiply the mass flow rate, then we find the absolute the amount of heat addition work done, etc. So let us find the efficiency. What is the efficiency? So generally, here we are discussing first efficiency, since we know that there is two efficiency can be defined in two ways, in the terms of energy and in the terms of exergy. When we apply exergy analysis, this is called second life efficiency. But we are just discussing the first life efficiency. So the first life efficiency is the work output, how much output we are getting, and the how much input we are supplying. So what is output? So here output is the work developed. So how much work is developed? So work is developed in the turbine, that is positive work, and in compressor or pump we have to supply some work. So the network is the turbine work minus pump work, that is W net. So upon the heat supplied, that is heat input, so in that way you will find the efficiency, thermal efficiency of the power plant, that is W net upon Q. This W net can be calculated in two ways. Either you will find Wt minus Wp, or we can say that is Q1 or Qin, that is heat supplied in the boiler minus heat rejected. Because since this is the cycle, and the cyclic algebraic sum for any cycle, algebraic sum of all the heat transfer will be equal to algebraic sum of all the work transfer. So generally, in general, we define efficiency in the terms of 1 minus the heat rejected upon the heat supplied, or sometimes like W net, that is Wt minus Wp upon Q1. So in general, since in Rankine cycle, the expansion is of vapor and the compression or the pumping, the negative work is done on the liquid. So since liquid saturated liquid specific volume is very less as compared to the superheated vapor. So for low pressure cycle, here we can neglect the uh, negative work, that is the pump work. So if we neglect the pump work or negative work, then this efficiency will become Wt upon, that is Wt upon the Q in, that is heat input. Why we are neglecting pump work? Because this pump work is very uh, less as compared to the turbine work developed in the turbine. So, yeah, so let's suppose if turbine work is in the range of 1000 kilojoule per kg, so this pump work will comes out in 2 to 3 kg kilojoule per kg. So the pump work is generally neglected for the low pressure cycle. If it is written in the problem, then no problem. If it is not written, even if it is not written, you just write simply neglecting pump work, and you, you can go for further calculations. But uh, carefully read the questions. If it is written like find the network, find the work ratio. If it is asked, work ratio is asked, in that situation, even if the operating pressure is very moderate or very low, in that case also you have to find the pump work. So to neglect pump work, just consider two to three things. See if W net is asked, see if pump work is asked, or see if work ratio is asked. In that, in three situations, you cannot neglect the pump work. You have to calculate pump work. Otherwise, you can simply just write a sentence neglecting pump work, and you can neglect pump work. You will get 100% marks. Nobody will deduct any marks. But if work ratio is asked, you have to calculate the pump work and work ratios. Generally, work ratio in the vapor power cycle or Rankine cycle, it comes in the 99%, something 98%, 99%. But in the case of gas turbine, since the compression and expansion both are of gases, so in the case of gas turbine, it comes out in the range of 40%, 50%, 60%. So, but in the case of Rankine cycle, it is generally work ratio comes out 98%, 99%. So, what is the work ratio? Work ratio is W net upon the work developed in the turbine, WT. W net upon WT. So, since W, if we neglect pump work, then W net will become WT. The WT by WT, that is 100%. Yeah. Okay. So, let us move further. That is the ideal Rankine cycle. So this is the how we say this. The cycle is the ideal cycle. There are four processes. So isentropic, the compression in the pump is that is isentropic, that is reversible adiabatic. Similarly, the heat addition is isobaric. Expansion in the turbine is isentropic, that is reversible adiabatic, and the heat rejection is also isobaric, that is the constant pressure heat rejection. These are the this is the since Rankine cycle is the ideal cycle, that is why yes. So let us discuss the regenerative cycle. So what happened? Let us see the point 6. See the point 6 on the schematic diagram as well as the TS diagram. So at point 6, what happened? We extract M1 kg of steam, M1 kg of steam at pressure P2. See the TS diagram at P2, we are extracting the steam at point 6. How much? M1 kg. And remaining 1 minus 1, uh, remaining 1 minus M1 kg steam is expanded up to the condenser pressure. So at 7, we will have 1 minus M1 kg of steam. And now this steam enters the condenser. How much? 1 minus M1 kg at state 7 enters the condenser where it is condensed. And after condensation, this saturated liquid at state 1 is pumped to the saturated liquid at state 1 is pumped to the pressure P2 in the heater. So since we supply this liquid 1 minus M1 kg into the heater, and M1 kg steam is bleeded. So here in the heater, what will happen? This 1 minus M1 kg steam is this M 1 minus m1 kg steam is heated and m1 kg steam is condensed. So we bleeded steam in such a way so that the after the heating, the temperature of this steam will become the saturation pressure or saturated liquid at state 3 or at pressure P2. So see here the example, the in the heater, this is the closed type of heater. Heaters are of two type, closed and open. So this is a closed type of heater. So the water 1 minus m1 kg water is in the pipe and that is surrounded by the steam, m1 kg steam. Since all the steam is condensed, this condensed steam is further mixed. This condensed steam is further mixed and the 1 kg saturated liquid is produced at state 3. This 1 kg saturated liquid, this 1 kg saturated liquid is further pumped to, this is pumped to state 4 in the boiler. And see here in the boiler, what happened? Further, isobaric heat addition takes place and this steam is generated at state 5. This is further supplied to the turbine. In this way, cycle is repeated. So, in this case, just see what will happen if this cycle will be the simple Rankine cycle. So, what will happen in this simple Rankine cycle, the heat addition would be from state 2 here. And now, by simply regenerating, simply using just one heater, this heat addition in the boiler start from state 4. So see, so instead of state 2, we are heating from state 4. So the mean temperature, or we can say the average temperature of heat addition will increases, therefore the efficiency of the cycle will definitely increases. So in this regenerative cycle, what will happen? The mean temperature of heat addition increases, therefore the efficiency of cycle is further increases. But there is the problem. You can see the problem from, since here we are extracting, or we can say bleeding steam m1 kg. So there will be lost work. We will, the efficiency will increases, but the capacity of the plant will be decreases. How much? See here from 6 to 7, there is only 1 minus m1 kg of steam. So therefore, there will be somewhat less amount of work produced. So the work developed will be H5 minus H6 plus here in the lower section, or we can say the low pressure turbine from pressure P2 to P3, PB, the expansion takes place of 1 minus m1 kg. So work done will be 1 minus m1 kg here, 1 minus m1 kg into the H6 minus H7. If in the simple Rankine cycle, it will be the simply H6 minus H7. So H6 minus H7 into m1 kg of work is lost. So we will get somewhat less work, but the efficiency will be higher. So in the regenerative cycle, see, if we are not increasing the steam supply, what will happen? The capacity of the plant will reduce. The capacity of the plant will definitely reduce. Another problem of this regenerative cycle is the excessive moisture in the, so this excessive moisture will damage the turbine blades. So this is another problem of the regenerative cycle. But in the actual power plants, this regeneration is always associated with reheat. So if we combine regeneration with reheat, then this problem will also be solved. So in actual practice, in the modern day power plants, we are using the Rankine cycle with reheat and regeneration. In that way, the efficiency is maximized. Again, another cycle is called, okay, that's it. Let us go to the next cycle. Next. let us see this the combined cycle. So what happened in the combined cycle? See, if we are having a gas turbine power plant, so in this the gas turbine, what happened? The turbine exhaust is excessively of high temperature. So if we apply a heat exchanger, or we can say the cascaded heat exchanger, if it is the for the gas turbine power plant, it is the heat rejection, means we are cooling the turbine exhaust, and with the help of this turbine exhaust we are generating steam, and this steam is supplied to the steam turbine for the power production. So this type of cycle is called the combined cycle, means there are two cycles. This is not binary cycle, this is combined cycle. What happened? The upper cycle is, or topping cycle, this is called topping cycle. Topping cycle or upper cycle is a gas turbine cycle working on the Brayton cycle, and the bottoming cycle at the lower cycle is the Rankine cycle, simple steam power plant working on the Rankine cycle. So see here, the gas turbine plants, heat exchanger, or we can say the heat rejected by the gas turbine is uh, utilized for the steam generation in the Rankine cycle, or we can say the this is the act as a boiler. So we can say the flue gases for the boiler are the exhaust of the turbine, gas turbine. So we can say for in the boiler we fire the coals, and flue gases are generated. These flues are used to generate steam. Here we are not firing any. We are not firing any fuel. Here, what happened? We are just using a gas turbine exhaust to generate steam, and this steam is used to generate steam, and this steam is supplied in the steam turbine to generate work. This type of cycle is called combined cycle, and this increases the efficiency. Suppose if the efficiency of the first cycle is neta 1 and efficiency of second cycle is neta 2, so the combined efficiency of both the cycle will be the greater than like neta 1 plus neta 2 minus neta 1 neta 2. So in this way the efficiency of the heat engines are improved. Okay. Okay, I think it's enough for today. Okay, thank you so much. Thank you. 5.